Hey everybody, so we're going to do another volume of rotation, though this one's going to have a little twist to it as like the last one did. So what we're going to do, we're looking for the volume of the object constructed by rotating the region enclosed by these two functions, y equals 1/2 x and y equals the square root of x, around the y-axis. So in this one, we're rotating around the y-axis instead of around the x-axis. So let's get a picture of this object, and I want to start by understanding what the first the region, and then what happens when we rotate that region. So I'll throw out a couple of axes. I'm going to put the y-axis in this time since we are going to be rotating around it. And let's draw our function. So there's our two axes. So I've got two functions here, y equals the square root of x, which is going to look something like this. Extend it a little more. And then the function y equals 1/2 x. So I only care when it says the region enclosed by these, so I'm looking for some section that's completely surrounded by these two graphs. Since this function only exists on the positive x-axis, I'm not going to, the line y equals 1/2 x, of course, goes in both directions, but I'm only going to draw the part that's relevant to this shape. So this graph is going to look something like this, right? So these are our two graphs. Let's label them. This is y equals, this one's the square root of x, and this is y equals 1/2 x. Okay, so there's our region. And then when we rotate it, so what I'm going to do is draw sort of the mirror image. So you'll have to imagine this thing, right, spinning, spinning around the x-axis. I don't know how to indicate that any better. I don't know if those are helping. But so we'll create a new shape, and what I'm going to draw is first the mirror image of this on the other side of the y-axis as best I can. Okay, so it's not perfect, but you get the idea that, like, if we took, for instance, this point here and rotated around, we're going to create this hole, and then there would be similar shape in the front, right? So it's kind of a bowl that gets pointy at the bottom on the inside, and from the outside it would look like a pyramid, sort of upside down pyramid, more or less, like a cone, I should say. All right, so there's our picture, right? So this is different than other ones we've seen in the following way. If I slice this up, what we've done in the past is slice things up in the x direction because they've been rotating around the x-axis. And when we slice in the x direction, or make a vertical slice, I should say, we get these circular faces. But to get a circular face, I would need to, in this case, slice in the y direction. So if I sliced this like this, right, this is kind of the shape going backwards, and we would have the same thing coming forward, right? There's this circular, if you slice it, there would be this circular shape, right? It's like slicing a bowl or something like that. But it's in the y direction now, so things are behaving a little bit differently, okay? So let's think about this shape right here. If I pull this disc out, this ring, what I want to do, right, I'm going to construct an area function for this ring. But now my area is going to depend on y instead of x. Okay? I'm going to, for instance, the area of the ring at the bottom would be 0, and the area of the ring at the height of this intersection would also be 0 because there's no real ring. In the middle, it gets widest somewhere in here where you have largest area. Down here, if we sliced it, we'd get a very small area, and so forth. So depending on the y value, as we move up and down, we get different areas of these rings, right? So the area or the washer, I guess I called it last time. The area would be pi times the large radius squared minus pi times the little radius squared, where the little radius is just the distance there, the big radius is the distance there, which we did last time. We factored out the pi and got this nice little formula, okay? But now I want this to be a function that depends on y. In other words, I want to come up with a way to write this as a of y, right? And each of these radii should depend on which y value we choose. So we want to figure out how to make that happen. So let's look closely at our picture. This little radius right here is the distance from the x-axis, sorry, the y-axis to this first curve. That's where that distance comes from, right? So it's the x-coordinate of this point here, right? But I want it in terms of y. Well, if I have a y value, remember that point is on the curve. This is on the curve y equals the square root of x. This green distance is the x-coordinate of that point. But at that point, the x-coordinate is y squared, right? So for instance, let's think of one point on the curve, this y equals the square root of x. So maybe something like the point, if x was 1/4, y would be 1/2. Notice that y, this 1/2, is equal to, x is equal to 1/2 squared, okay? All right, so that tells me that this inner radius, whose distance is x, can also be written as y squared. So this first, so the little radius is y squared, and then we're squaring the little radius, okay? All right, now the big radius, big R, that's the distance from the x-axis out to this curve. Same idea, that the distance is actually the x-coordinate of this point, but along the curve y equals 1/2 x, we know x equals 2y. Those are equivalent statements just written in the other direction. So this big radius is going to be, capital R, is going to be 2y, and then we're squaring it, okay? So there's our area function, but we're now doing it in terms of y, okay? Now, that means we can set up our volume equation. So our volume is going to be, we need to know, we haven't figured out yet what boundaries we're going to go from, but we know what it looks like, pi times 2y squared, 2y squared minus y squared squared dy. We're integrating in the y direction now. We're using all the same principles, all the same ideas. We're just turning our head to the side, right? It's really essentially like that. We're just thinking about it in the opposite direction, where we're thinking of y as our input and x as our output. But every argument we've ever made about the x value, we can make about the y value in the other direction, okay? All right, so we can clean this up a little bit. So actually, let's move that pi out front just to simplify things. So pi's out here. I still don't know my bounds. We'll do that next, but let's just write this as 4y squared minus y to the 4th dy. So there's our integral. Now we need to know what our bounds are. We're not adding up as we move along the x-axis now, though. We're adding up, we're integrating as we move along the y-axis. So we need to know, it's clear from the picture, though we'll prove it in a moment, that they intersect at 0. We need to know how high we're going to go. In other words, we need to know this y-coordinate over here. So to find the intersection of these two curves, we need to know where we can do it in terms of x or y. Let's do it in terms of y, since that's what we're looking for. We want to know where 2y is equal to y squared. You might see the result, the answer to this. We could also solve for this, noting that 2y minus y squared equals 0. Factor out a y, we get 2y times 2 minus y equals 0, which gives us two solutions, 0 and 2. All right, so that's this point here has a y coordinate of 2, which means x has a coordinate of 4, though we don't need that to do this problem. Okay, and then we know that they also go through the point 0, 0. So those are our two intersection points that define, give us the boundaries for this integral. So let's go ahead and compute the integral. So we're going from 0 to 2, 4y squared minus y to the 4th dy. This is pi times, we take an antiderivative. I'm going to get 4y cubed minus y to the 5th over 5. Evaluating this from 0 to 2. This is nice. The 0 is going to go away. And so we'll get, let's see, and I put 2 in here. I've got 4 times 2 cubed, so that's 2 to the 5th minus 2 to the 5th over 5, which is going to be, so let's see, we could say this is 4/5 times 2 to the 5th. I don't know for sure if that's the easiest way to do it. Oh, I forgot something. Sorry, pardon me. Let me erase a couple of things. I knew something wasn't adding up from when I did this a moment ago. I took the antiderivative wrong. Let's just go back a couple of steps. This is looking too big. Oops. This antiderivative, sorry about this. The antiderivative should be pi 4/3 we should have there. Pardon me. We added our exponent to 3, we need to divide by it. Okay, so now we substitute in 2. So 4 times 2 cubed is, or 2 squared times 2 cubed, there's my 2 to the 5th over 3 minus 2 to the 5th over 5. I can factor out 2 to the 5th, which is 32 times pi. I've got 1/3 minus 1/5, which is 5/15 minus 3/15. So 2/15 times 32 gives me 64/15 pi. And that's that. Okay, so that's it for this one. It's a neat idea that we can change perspective, right? There's really nothing special about X or Y, and there's nothing special about the horizontal and vertical axes. Those are just choices that were made early on in the history of math that everyone now lives with. And it's easy enough to switch perspectives, and we're making all the same arguments, just using Y as our independent variable in how we're thinking about it. Okay, that's it. Thanks, everybody. See you next time.